Welcome to this lecture on arithmetic trees. In this lecture, we're going to take a break from talking about plain binary search trees and talk about using trees for another application, which is in this case is to model arithmetic or arithmetic expressions. And we'll talk about how to convert infix notation expressions into arithmetic trees and also how to evaluate them. So we can express arithmetic with trees. And we have two types of nodes in the tree. We have one type of node for operands, which are things like numbers or variables, and these are always leaves because they have just a particular value. And then we have operator nodes, which are internal nodes which operate on the values of other nodes. So for example, notice that the internal nodes plus times plus times plus times here, these are all internal nodes, and that all of the leaf nodes are operands. These are all values. And this tree right here represents the expression you see up here, 7 plus 6 times 4, etc. And you can map each of these operators to a node down at this tree. And you'll notice that the root of the tree is a plus, which happens to be this plus right here. Those two correspond. And this multiplication here corresponds to this multiplication down here, and this plus corresponds to this plus. And you'll notice that the deeper into the tree it is, the higher precedence it has. We do 6 times 4 before we do 7 plus that quantity, and therefore this subtree gets evaluated first before this subtree, right? And that's according to our rules of precedence. So we could map each of these operators onto these nodes. So again, we have this multiplication is the last thing that happens over here. So it's this one, and this addition is the second last thing that happens, and this multiplication is the first thing that happens. And so we can map them here like this. And so this tree represents exactly the same expression with the same precedence and has the same value as this statement. But the advantage here is that if we can represent it as a tree, then maybe we could manipulate it and understand the dependencies and the syntax here even better. If we had a tree that looked like the one that we saw on the previous slide, we would have to represent it using some C++ classes. So let's take a look at what those might look like. First of all, you'll notice that I mentioned two classes, but we're actually going to use three. And the first one is called an arithmetic node. And this is a class that has no data members, and it only has one function or method. And notice that that is a virtual function. In fact, it's a pure virtual function. We've got this equals 0 here that tells us that there is no implementation for this function. It is here only to provide an interface for other classes which subclass or derive from this class. So you'll notice the function is called eval. It takes no parameters, and it returns a double. Okay, so basically what this base class is doing is it's setting up for us a base class for any node in the tree which can evaluate itself. And if you think about the value of an operand, which is like a number or a variable, the value of an operand is just its value. So an operand node in this case is going to have a data member which is its value. And when we want to evaluate that, we just return that value. Okay. And the more complicated case, of course, is these internal nodes, which are operators, which take, in this case, every operator that we're talking about is a binary operator, so it will always have two children. We could have operators that were unary operators or trinary operators, but right now we're just doing addition, multiplication, subtraction, and division. And so these are all binary operators, so they all have two children. So an operator node has to know three things. The first thing that it has to know is what type of operator is it? Is it and in this case, it could be an addition, subtraction, multiplication, or division. And the second and third things that it needs to know are what are its left and right children that whose values it's going to operate on. Okay, so this is for this type of node, which is an operator like a plus or something. Okay, now the eval function for an operator has kind of two stages. The first stage is, notice it evaluates the left and evaluates the right. So if I'm calling eval on this node, the first thing that it does is it's going to call eval on the left and then call eval on the right. And once it has the value for the left and the right, then it can compute the value for this node. So once it has left value and right value, it's going to compute its own value, v, as either LV plus or LV minus RV, and so on and so forth. So you can see we're just doing a switch on the type of operator, and then we compute the value based on the type, and then we return the value here. Okay, so this is most of the logic that you would need. Aside from constructing a tree, once you have the tree constructed, you can evaluate it just like this. And this is almost all the code you would need to do that. So it's pretty short and simple. We already touched on this, the fact that the abstract base class is abstract to provide an interface for both the operand node, which, by the way, I should have emphasized, derives from the arithmetic node, as well as the operator node derives from the arithmetic node. And you'll notice that the children of the operator node are arithmetic nodes. In other words, the type here is an arithmetic node pointer. Okay. Now, why is it an arithmetic node pointer? Because an arithmetic node, an operator node, can be operating on values like 3 or 5, or it could be operating on the values of other subtrees, which are operators. So an operator can operate on the value that comes from an operand or another operator. So using this class hierarchy, we are able to represent both or either with an arithmetic node. So an operator node doesn't know which type of child it has, but it doesn't really care because all it has to know is that it's an arithmetic node which can evaluate itself. And the last question I have for you to think about, and pause the video and think about this for a second. What type of tree traversal does eval do? And in particular, what does this eval do? What type of tree traversal is this? Well, this tree traversal, before it can evaluate the node itself, has to know the value of the left and the right nodes, and then it can compute its own value. So when you evaluate a node, the first thing it does is evaluate the left and then the right and then itself. So that's a post-order traversal, post-order. Now, how would we construct a tree that looks like this? How would we construct an arithmetic expression tree? Well, we can reuse an algorithm that we've already looked at, the shunting yard algorithm, Dijkstra's shunting yard algorithm, which converts infix to postfix. And in this case, we're not going to convert infix to postfix. We're going to convert infix to a tree. And the shunting yard algorithm uses one stack to convert infix to postfix, and that stack is for operators. But in this algorithm, we're going to use two stacks. One for operators, just like in the regular shunting yard algorithm, but the other one is for trees. And we're going to build up larger and larger trees on this stack. It's kind of like what you might call an accumulator stack that we used in the postfix calculator that we talked about several lectures ago. So the main algorithm looks like this, and we'll illustrate this on the next slide. We're going to read each token left to right in the infix expression, and for each token t, we're going to differentiate whether t is an operand or an operator. If it's an operand, just create an operand node, in other words, a tree node, which is an operand, and push it onto the tree stack. Okay? When we were doing infix to postfix, this is kind of like just printing out that value. But here we're pushing it onto a tree stack. But if t is an operator, then we're going to push that operator onto the operator stack, like we did with the shunting yard algorithm. But if there are any equal or higher precedence operators on the operator stack, we pop those first and process them. And then once we're done reading all the tokens, we pop any remaining operators. Now, every time we pop an operator from the operator stack, we do the following things. So in other words, when we pop an operator here or here, we do the following things. We create a new operator node of the type that we just popped off the operator stack. Okay, so we create maybe a new plus. And then we pop two trees from the tree stack, the top two trees, and we make them children of the operator. Okay, this is the first one we pop, and this is the second one we pop. Okay, And then we push the operator node that we just created onto the stack. In other words, we push this thing back onto the stack. So this is why this is a stack of trees. Okay, so let's take a look at what this actually looks like. And by the way, this 1 and 2 here, these are the first and second things I popped off the tree stack. These could be themselves, trees that had children as well. So let's take a look at what this looks like in a real example. I think this will make it clearer for you. So we're going to follow the rules that we just talked about. We're going to read these tokens from left to right, and we'll start with 7. So when we read 7, that is an operand. So we're going to create a node for that, put it there. So this is my tree stack, and the tree stack is going to kind of roughly run this way, and my operator stack is also roughly going to run this way. Okay, so from bottom to top going this way. Then I read a multiplication, and of course that's an operator, so I push it on my operator stack. Then I read a 6, so I'm going to create a new operand node and push it onto the tree stack. So now I have 2 items on my tree stack, 7 and then 6 is at the top. Now I read subtraction or minus sign, and I want to push it onto the operator stack, but I can't push subtraction on top of multiplication because multiplication has higher precedence. So the first thing that I have to do is pop off the multiplication, use it to create a new node, and then pop off 6, then 7, and make them children of the multiplication node. And then I push back onto this tree stack this node right here. So now my tree stack has only one item on it. It's one tree, and it's this tree right here, which is rooted with a multiplication symbol. Okay, so this tree is not going to be linear when I draw it. I hope it'll make sense anyway. Now, remember, the last thing I did was I read this token, so I still have to push that onto my operator stack, so I'm going to do that now. The next thing I read is a parenthesis, which I treat specially, and I push it onto my operator stack. Then 3, I'm going to create a node for that and push it onto my tree stack. Then plus goes onto my operator stack. And then 2 goes onto my tree stack. And then multiplication. Now multiplication can go on top of this operator stack because multiplication has higher precedence than addition, and that's okay. Then 5, I'm going to create a new operand node. And then when I see the closing parenthesis, I'm going to pop everything off this operator stack until I get to this closing or opening parenthesis. So when I pop off this multiplication, I use it to create a new node, and I pop off the top 2 things on the tree stack. Now notice, before I do that, before I go there, notice that right now on the tree stack is this tree, this tree, this tree, and this tree. So I have 4 things on my stack. So when I pop off the multiplication, I'm going to create a node, pop the top 2 items off this tree stack, create, put them as children of the multiplication node, and then push this subtree or this tree back onto the stack. So now my tree stack contains this tree, this node, and this tree. Now I still have to pop the plus off, so I pop the plus off, I create a node for it, and then I'm going to pop the top 2 items off my tree stack, which are this and this, and I'm going to create or make those children of that node, and then I'm going to push that tree back onto this tree stack. So now my tree stack has exactly 2 things on it, this tree and this tree. Okay, now I'm still popping things off until I get to the open parenthesis. I've gotten back to the open parenthesis, so I'm done processing that close parenthesis now. Okay, that was a lot, I know, but basically this close parenthesis caused me to pop off this and this and this off the operator stack and use them to build these subtrees. Now, what's on my operator stack? On my operator stack, I still have this node, right, or this operator right here, okay? And on my tree stack, I still have these 2 trees. So I read the next token, which is multiplication, and I'm going to push that on my operator stack. Now, I know my operator stack looks a little ugly right now. There's only 2 items on my operator stack. Ignore the fact that I've sort of deleted these in line. There's only just the subtraction or the minus and the multiplication. Next, I read 2. I'm going to create a node for 2, and then I'm done reading all the tokens, but I still have these 2 items on my operator stack. So I'm going to pop them off uh, top to bottom. So I pop off the multiplication, and I use that to create a new node, and I pop the top 2 items off the stack of the trees, and I make them the children, and I've now popped that off. And last but not least, the minus, and I pop the top 2 items off my stack, my tree stack, and they become the children of the minus. So now I have a tree that represents this operator, or this infix expression. And you'll notice that it is still 7 times 6 minus the quantity 3 plus quantity 2 times 5, all times 2. So these have the same value. These represent the same expression. You'll also notice that just like the shunting yard algorithm was when we converted infix to postfix, this is a linear time algorithm. So we went through this expression from left to right, and for each token rather, we created a new node, and we may have popped and pushed one or two items, but a fixed number. So we can convert this into a tree, this infix expression into a tree that represents the same expression in linear time, which is really nice. Now, how could we go beyond what we've just seen? You could use this with more than just binary operators. You could use any functions you like. You could add the sine function, the cosine function. You could add negation. You could add exponentiation. You could add functions that take multiple parameters. In addition, you could model variables and not just constant values. So everything that we've looked at today had constants like 7 and 6 and 3, but you could model variables like x and y and z. And then you could create a tree that represents this function. And then every time you update the variables, change the value of the variable, the whole tree, the whole expression gets a new value, and you could evaluate that easily because you don't have to reparse the expression. The expression is already parsed into a tree. You change the value of those variables, and you get a new value for the entire tree. Finally, if you're interested in things like genetic programming, which is under the umbrella of artificial intelligence, you can use these types of trees to represent miniature functions or programs that you can then easily modify to get different genetic programs. And you can have many different functions or many different programs that are represented as trees, and then you could sort of evolve them by sort of taking this subtree from this one and this subtree from this one and swapping them or joining them together with a common root or something like that. And you can mutate them however you like. And you can use this for a type of genetic programming if you're trying to fit a model or a function to a bunch of data that you already have. So that's it. Those are arithmetic trees, and it's just one glimpse at how you could use trees for something other than just organizing or sorting data.